So in this video, I'm going to talk about briefly what object pose estimation is all about, especially regarding deep object pose estimator, which in the next video I'm going to explain the uh, for which the neural network architect. I will explain the neural network architecture in the next video. But right now, I just want to talk about what this network is actually getting as input and the outputs that it is calculating. And then in the next video, I'm going to go to more details about this neural network architecture. So as input to the neural network, it gets an RGB image, and the task is to detect these 3D cuboids surrounding my target object. Now these 3D cuboids are made of 8 points, as you can see in here, and from if you can detect these 8 points that make up this 3D bounding box surrounding your target object, then from there you can calculate the object pose using perspective endpoint algorithms, well established algorithms to algorithms. So by pose estimation, we mean detecting the rotation and translation matrices of the object from the camera coordinate system. So rotation means that the three rotation associated with my target object, which are roll, pitch, and yaw. And translation means three more parameters, which are the distance of this object in x, y, and z axis directions from the camera coordinate system. So these are 6 parameters. So now from these 8 points or this 3D cuboid, we are trying to find out 6 variables, and as a result, we call this 6 degree of freedom object pose estimation. So this is the objective. We will get an image, and we will have to predict this 3D bounding box surrounding my target object. This is what DOPE architecture does. Now let's talk a little bit about this how loop architecture in a high level view calculates the position of these points, and also some direction information associated with each of these vertices. So this is the neural network architecture for DOPE. I will not go into details of this neural network architecture. I will mainly focus on what it gives as output and what it gets as input. So let me just so as input, it gets an image of W by H by 3 size, that is width, height, and 3 channel of color channels. This is the input, and as output in here, actually this same output is received from these parts as well, but I'm just going to show from in here. So in here we get 9 image output. This chain is called belief chain. Belief belief maps. So you get 9 belief maps, each of size W by 8, H by 8 size. And in here, in this chain, this chain number 2 is the affinity map chain, and they calculate affinity maps, and we get 16 of them, or you may say that we get 8 pairs of them. Okay, so but what do these belief maps mean? Ideally, belief maps should look like something like this. Something like this. Ground truth belief maps look something like this. It will have black all over, and then it will have a bright spot at a particular location. But this location represents is the predicted or the ground truth location of in individual vertice or centroid. So let me elaborate that with simple drawing. So let's say that right now I'm talking about the belief maps only. So in belief maps, we will get sorry. So we will be getting so we will be getting 9 belief maps. One belief map, let's say this is the predicted belief map. Then there is the second predicted belief map. Similarly, we will get 9 predicted belief maps. Uh, and let's say that this is my target object. This is my target object. Actually, presentation purposes, yes, is this one. So this is my target object, and let's say this is vertex number 1. So the belief map number 1 will have a bright spot in here corresponding to this vertex position, and all around everywhere else it will be black. So eventually it will look again something like this. The location of the bright point will be on the top left corner, somewhere like that, somewhere there. Similarly, let's say that this is the second vertex location. As a result, the second belief map will have a bright spot that represents the location of the second vertex point in here. Same thing, and that way we will get total 8 belief maps corresponding to 8 vertex locations, and the ninth or the last belief map will represent the cuboid or the centroid of this cuboid. Centroid means the center of this cuboid or cube volume, and it will be somewhere in here. Just focus up in here. It will be somewhere in here. So that's how we get the predicted locations by the network, predicted locations of the vertex locations. But then if we can detect these vertices, then what is the need for these 16 affinity maps? So these 16, now I'm going to talk about the affinity maps and why do we need them. You may call them, instead of 16, you may call them 8 pairs. 8 pairs of image. Each pair will consist of 2 images, one corresponding to x-axis, one image corresponding to y-axis. So eventually we sort of merge these 2 images up and we end up with a single image. Just for understand our presentation purpose, I'm saying that we end up with this 8 images or 8 pairs of information. Now these 8 pairs corresponding to the 8 vertex. So these 8 pairs will represent, just like belief maps, will correspond to each vertex, not the centroid. Now, why do we need them? So let's just start out with this example in here. So let's say that this was my input image and I had detected an object in here. You see the 3D cuboid, it's perfectly in here. And I have another object in here, which is 3D cuboid in here. Now, if you look closely in here, you have detected a vertex point in here, you have also detected a vertex point in here, but this vertex point on the left belongs to this object on the top, and this vertex point on the right belongs to this object on the bottom. But how does a neural network tell us that which vertex belongs to which centroid, or where does their centroid what is the vector field information that gives us an information regarding like which centroid does each vertex belong to? And that's where the affinity maps come in. Again, I'm very much simplifying this explanation just for presentation purpose. So in this case in here, in my drawing, so let's say that I had another object in here. Up again. Okay, I'll just do it in here. Okay, so I had another object in here. From the belief maps, I also know the vertex locations. But how do I know that this vertice belong to this centroid and this vertice belong to this centroid? That's what these 8 feature maps, 8 vertex maps gives us. 8 affinity maps give us. So the first affinity map will correspond to the top level vertex point in here. It will give a vector field information like this. As a result, so the image will look like something like this. Again, I'm simplifying it a lot. So the first affinity map will have a vector field information like this, which represents that where does this vertice belong to, where does this vertice belong to. Same goes for all the other vertices. I will get, for each vertice, I will get a direction information which tells me where does the corresponding centroid exist for each of these vertices. As a result, now I can resolve this ambiguity. Same goes for me here. If I had a vector field information for these 2 points, a vector field indicating towards this direction and a vector field for this point indicating towards this direction, then easily I can solve this ambiguity, right? So that's why we need eight pairs of this affinity maps, which gives me direction information. As a result, now I not only know that the predicted location of the vertices and the centroid, I also know which vertices belong to which centroid without any sort of ambiguity. And that's how the neural network architecture assists us in detecting the 3D cuboid, and from there we find out the pose. Now, one thing I want to just emphasize before going on to more details, this output in here is not the only output that, okay, let's just not continue on that. I will continue on that in the next video about the neural network architecture. So this is what I wanted to talk about. So conclude the video. The dope gets as input a color image of W by H by 3 size. Then it detects 9 belief maps as shown in green, and then 16 or affinity maps, or you may say 8 pairs of affinity maps that gives us a vector field information for each of the vertex locations. Thank you for watching the video.